Let's begin with our today's topic of class 12th physics. The today's topic is charge and its properties. So to begin with, let's have an introduction of this particular topic, that is of electrostatics. Now what is electrostatics? Electrostatics is the branch of physics which deals with the study of forces, fields and potentials arising from static charges. This word electricity is derived from the Greek word electron, which means ember. So first of all, the electrostatic, how it was observed by Greek philosopher Thales of Miletus. When he observed that ember is rubbed with wool, it attracts the light objects. So we are having one activity using comb and paper to show how that electrostatics was observed, that we can have a charged comb and the pieces of paper. Now when this charged comb is brought near the pieces of the paper, it is observed that the pieces of paper get attracted towards the comb. It is just because of the static electricity. Now let's see, there is another activity which you can have using the plastic scale and the paper bits, in which we have to take a plastic scale, and if it is a charged one and if it is brought near pieces of paper, the pieces of papers get attracted towards it. It is again because of the static electrostatics. Now further, what is the application of electrostats that we have learned just the introduction. So it is used in the electrostatics loudspeaker, in flash connection of chimneys, in Xerox copying machine. So now next, what we are having, the electric charge. The new topic will be the basic topic that we have to start is the electric charge. Now mind it, the charge is a scalar physical quantity that is associated with matter, due to which it produces and experiences electrical and magnetic effects. That is our concern in this particular 12th class. In all the coming part 1 book, we will be dealing with the electrical and magnetic effects. Now, an obvious question comes to mind: what is the origin of charge? The origin of charge, or the cause of charging, is the actual transfer of electrons from one material to another. Now mind it, the key word here is the actual transfer of electrons. Now what is meant by this actual transfer of electrons? Let us see. If we are having a neutral body, in neutral body we know that the number of electrons and number of protons are always equal. But when this neutral body changes to a positively charged body, how it can become a positively charged body? It is just by donating the number of electrons. So by donating, what we can have, number of electrons will always be less than the number of electrons. Thus a neutral body can become a positively charged. So keep this in mind. Whenever the electrons are donated, the body becomes positively charged. Now how this neutral body can become a negatively charged body? It can become a negatively charged body by accepting the electrons. So for this negatively charged body, mind it, the number of electrons will always be greater than the number of protons. Thus we have seen the two types of the charges. What are they? One is positive and the other one is negative. So a neutral body can become a positively charged body, or it can become a negatively charged body. Now the other consequences that is related with the charge is called again as the mass. Now what happens to the mass of a body? If we are having a neutral body of mass m, and when it becomes a positively charged body, what will happen? By donating the electrons, it has become a positively charged body. So what will happen? Naturally, now its mass will be, new mass will be m dash, which will always be less than the original mass of a neutral body. Now another case, if the same neutral body, let us suppose it gets converted to it becomes a negatively charged body. Now we know that how a body can become a negatively charged, by accepting the electrons. Now by accepting the electrons, since electrons are accompanied by masses, so this negatively charged body, its new mass will become m dash, which will always be greater than the mass of the original neutral body. So keep this in mind. Whenever a neutral body becomes a positively charged, its mass is always lesser than the original mass, and when a neutral body becomes a negatively charged body, its mass always becomes a greater than the original mass. Now next, our topic will be the methods of charging. Now there are the three methods of charging. What are they? First is rubbing, second is charging by conduction, and third is charging by induction. So let us first concentrate on each of them one by one. So first we will be having rubbing. So what is rubbing? Rubbing is basically the charging by friction. So in rubbing, what we have to take? We have to take one glass rod and one silk cloth. When these two things are rubbed against each other, mind it, they are in physical contact and they are rubbing against each other. So what we will observe is that this glass rod will become positively charged and the silk cloth will become a negatively charged. Now the obvious question comes into mind: why this becomes positively charged? Because the rod would have transferred some of the electrons to the silk cloth. Keep this in mind. Whenever the electrons are transferred from the glass rod to the silk cloth, it becomes positively charged, and when the silk will gets negatively charged, because it has gained certain electrons from the electrons given by the rod. Similarly, if we rub an animal fur against the plastic rod, what we will notice is that animal fur will gain the positive charge and the plastic rod will gain the negative charge. Now you can answer this particular question, why animal fur becomes positively charged? Because it has donated or it has transferred some of its electrons to the plastic rod. Thus, the plastic rod which accepts the electrons becomes negatively charged, and animal fur which has donated the electrons becomes positively charged. Now, the explanation of this particular static electricity is the electron theory of electrification. What this theory explains, that electricity developed on bodies when two suitable bodies are rubbed with each other is called as the frictional electricity. Mind it, here the key word is that two suitable bodies are rubbed with each other, that is called as the static electricity. Whenever the two static bodies are rubbed with each other, this is the static electricity. Now, in order to electrify a neutral body, the neutral body can have the excess of charge, or it can be the deficit of the charges. Now, whenever what we can do, whenever a body is being charged positively, that is by losing some of its electrons, and a body can become charged negatively by gaining some of the electrons. So what is the key statement here? A body becomes positively charged by losing some of its electrons, and a body can become a negatively charged by gaining some of the electrons. So this is called as the electron theory of electrification. Now, next it is observed that whenever two glass rods are rubbed with a wool or a silk cloth are brought close to each other, they repel each other. Why is it so? Because both the glass rods have developed same kind of the charge, so it has been observed that they start repelling each other. Now, similarly, when we take the two plastic rods rubbed with cat's fur, they again repel each other. Why is it so? Because their two plastic rods develop the same kind of the charge. But it is observed that when a glass rod and a plastic rod are brought close to each other, they too shows the attraction. Why is it so? Because they too are oppositely charged. So based on this particular observation, the conclusion drawn is that the like charges repel and unlike charges attract each other. This is how we can show the repulsion, and this is the attraction part. There is another way that like charges repel, two positive charges will repel and two negative charges will repel. Similarly, the opposite charges, that is one positive and one negative, will attract each other. Next, the second method is charging by induction. Now, what happens in charging by induction? We have to take the two metallic spheres A and B brought close to each other. Now, we have to bring a charged rod. If we want to charge the two spheres, we have to bring a charged rod which is already positively charged. Because of this positively charged rod, what will happen? The free electrons in the sphere are attracted towards the rod. Mind it, here what will happen? The free electrons of the sphere A will attracted towards because of this positive charge, and similarly the positive charges of B get accumulated on the rear side of its rear side. So what this is called as the method of induction of charges, and it happens almost instantly. Thus accumulated charges remain on the surface. Next, what we have to do, if the two spheres are just being separated out, then what we will notice is that the sphere A will still having negative charge and the sphere B is still having a positive charge. Now, if we remove this plastic rod, this charged rod, what we will notice is that the charges on the spheres rearrange themselves, and on further separation, what we notice is that the charges get uniformly distributed over them. So, in this process, what we have noticed is that metal spheres will each be equal and oppositely charged. Keep this in mind. This will be your key statement. What is the key statement? Metal spheres, they will by induction, by the method of induction, they can be equally and oppositely charged. This question can be asked, how we can charge the two metal spheres equally and oppositely charged. This is possible only by the method of induction. So now let's have one knowledge test. Now what the knowledge test says is, how can you charge a metal sphere positively without touching it? Mind it, here the key word is positively. So in order to charge a sphere positively, what we have to do? We have to take one uncharged sphere, that is a isolated sphere. Now in order to charge this positively, we have to bring this negatively charged rod near it, so that the positive charges of this sphere get attracted towards this particular rod and negative charge get accumulated on the other side. When we ground this, all the negative charges will be grounded over in this particular direction, and the positive charges, again there will be the redistribution. So all this you have to explain in words. So this is how you can explain in detail how we can charge a metal sphere positively. Now the similar question that can be asked on this particular pattern is, how a metal sphere can be charged negatively. Mind it, here the keyword is negatively. So in order to charge a sphere negatively, we have to bring a positively charged rod. We have to bring a positively charged near it, so this sphere will develop the negative charge. So mind it, by the method of induction, always the opposite charges that get developed on the isolated body. Next question is describe how two metal spheres can be oppositely charged by induction. Now this question I have explained earlier in the form of article in the previous slide. So I think now you all will be able to solve it. Go for it. Now the next and the last method of charging is charging by conduction. Now what's the difference between this conduction and induction is that here we have to touch that two objects without rubbing. So there the two objects are in contact with each other, but we are not rubbing it. Mind it, the key word here is just they are in touch with each other. And in induction they were not in touch. There we were having the without touching them. So here what we notice is that when a charged body is brought in contact with an uncharged conductor, charge flows from the charged body to the uncharged body. This is the key statement over here. The charge will always flows from charged body to the uncharged body. See how this happens? If we have a charged body which is positively charged, this positive charge resides on the outer surface and we are having another uncharged body held at a separation. But now if the two bodies bring in contact, what we notice is that there is a redistribution of the charges, and now when the two spheres get separated, both the bodies become positively charged. So mind it, in case of a conduction, the body can be charged with the same sign. Keep this in mind. The body can be charged with the same sign, but in induction the bodies are charged with the opposite sign, opposite nature of charges. Next, let us come to the next article, unit and dimensional formula. The SI unit of charge is Coulomb, which is denoted by the symbol C. The CGS unit of charge is ESU, which is read as electrostatic unit. The dimensional formula of Q is equals to A into T. Next is point charge. Now this point charge name will be coming frequently in the chapter, so let us it's worth mentioning over here that what is a point charge? It's whose spatial size is negligible as compared to other distances, that is whose dimensions are negligible as compared to the other distances. Now let's come on to the general properties of the charge. There are various properties of the charge, so let us go for them. First is charge is a scalar quantity, charge is transferable, charge is always associated with the mass, charge is conserved, charge is invariance, charge produces electric and magnetic field, charges resides on the outer surface of the conductor, and the charge is quantized. Mind it, these all are the general properties. Now let us go for the basic properties of the charges that will be asked in the board. So if only three properties are being asked, so you have to mention these three basic properties of the charges. Let us see what are they. First is the additivity of the charges. The point charges are scalars. Mind it, the charges are always scalars. That means they are not having any direction, only the magnitude, and they can be added algebraically. What is meant by added algebraically? If your body is having number of charges Q1, Q2, Q3 are the point charges, then again here that is point charges. We will be referring to the point charges always because their dimension are very, very small or negligible. So the total charge on the body will become Q1 plus Q2 plus Q3 plus Qn. Charges have no direction but can be positive or negative. Let us see an example of this additivity of the charge. So we are having a one question check. A total charge on a system containing 4 charges. What are they? Minus 3 microcoulomb, 2 microcoulomb, 4 microcoulomb and minus 5 microcoulomb. So the total charge on the body will be what? The algebraic sum. That is, these numerical values are added with the help of their sign only. So the total charge on the body will become minus 2 microcoulomb. That is, the net charge on the body is negative. I hope this would be clear to you. So the next property is the basic property is the conservation of charges. Now the meaning of conservation is clear to all, that nothing is being added or nothing can be deleted, only the things is that transferred. So the total charge in an isolated system is always conserved, that is constant. We cannot add or we cannot remove. Only in an isolated system the charges get transferred from one body to another, but the net charge of the system remains the same. So during rubbing, basically what happens? No new charges are being created, only there is a redistribution of the charges. Now next, third property is the quantization of charges. Now this term will be new to all of you, those who are the beginner of the 12th class. So what is the quantization? That is, the charge is always represented in the form of Q equals to NE. Here this is the formula for the quantization of charges, Q equals to NE, where Q is the total amount of charge, N is the integral integer, and E is the charge on a basic elementary particle, that is electron. So the charge on an electron is 1.621 into 10 to the power minus 19 Coulomb. This is called as the quantization of charge. Now what is the cause of quantization? The cause of quantization is that during rubbing, only an integral number of electrons can be transferred. Keep that, this is the key statement. Only an integral number of electrons can be transferred. It means that either 1, 2, 3 or 4 number of electrons, or this is the integral number the electrons can be transferred, not in fraction. That is 1 by 2, half of the electron, 3 by 2 of the electron, 4 by 5 of the electrons will never be get transferred. That is what is meant by the quantization of charge. That means whenever the electrons are being transferred, they are always transferred in an integral multiple of E. Now, quantization is usually ignored at macroscopic level because at that point charges are taken to be continuous. Now, what is meant by macroscopic level? That means at large level the charges are so continuous that this integral concept can be ignored. That is, quantization of charge can be ignored and they can be treated as continuous. Now, next what we have, it is 1 microcoulomb is equals to 10 to the power minus 6 coulomb. Now, let's have one knowledge test based on this quantization. So, what the knowledge test is having for us, how many electrons constitute 1 coulomb of charge? So, here the key word is 1 coulomb of charge. So, number of electrons present in 1 coulomb of charge, how we can compute? By using the formula Q equals to NE. In this particular formula, we have to put the various magnitude. That is, the given question Q equals to 1 coulomb. We have to compute the number of electrons for 1 coulomb. So, value of Q will become 1 coulomb. Then electronic charge is 1.6 into 10 to the power minus 19 coulomb. So, on substituting these particular values in this particular given formula, we will get, and so on solving, we will get N equals to 6.25 into 10 to the power 18. See how many number of electrons, so huge, large quantity of electrons are present in only 1 coulomb of charge. So, at this particular stage, the quantization of charge can be ignored and it becomes a continuous quantity. That is what is meant by this. Now, the next question is, why can one ignore quantization of electric charge when dealing with macroscopic, that is the large scale charges? Now, what is the reason behind that? Because at macroscopic level, one deals with the charges that are enormous compared to the magnitude of the charge E. Just now I have shown you in 1 coulomb of charge, we are dealing with 10 to the power 18 electrons. So, it is such a huge amount that at macroscopic level, we are having an enormous or a large number of electrons, so that we can ignore, so that the charges can increase or decrease only in the units of E. Thus, at macroscopic level, the quantization has no practical consequences and can be ignored. Automatically, it becomes continuous. So, we can ignore the quantization of the charge. Whereas at microscopic level, where we are dealing with only few tens or hundreds of electrons, the quantization of the charge cannot be ignored. We have to keep on counting the number of electrons. This is all about what is meant by the negligence of the quantization of a charge at a macroscopic level. Here in this video, I will be teaching you about the concept and the derivatives related to Coulomb's law, and all the numericals concerned this Coulomb's law I will be teaching in the coming video. So, let's start with the concepts of Coulomb's law. Coulomb's law helps us to find the force between the 2 point charges. Now, what the key point here is that it always exists between the force exists between the 2 point charges. The name of the point charges I have explained earlier in my previous video. The concept of point charges, you may refer to that video. So, here now if we have two charges, that is one is Q1 and the other one is Q2 in a space or in vacuum, and they are separated by a distance r, then a force exists, that is a force of repulsion exists between these two like charges, and whose magnitude the Coulomb's law will help us to find it out. It states that the force is inversely proportional to the square of distance between these charges. It is directly proportional to the product of magnitude of the two charges, and it acts along the line joining the two charges. Now, here this statement is very important, that it always acts along the line joining the two charges. That means it always acts along this line. It never acts along this line. If we draw on this line, no, it is not. If we withdraw this particular line, no, again it is on this direction, it will not be acting. There is only one particular direction in which the Coulomb's force law will be acting. On combining these two factors, what we will get? F equals to K Q1 Q2 by R square. Where this? Because we have removed the proportionality sign, so we have to introduce one constant of proportionality, which is K. Now, the value of the K is 1 upon 4 pi epsilon naught. So, the formula for F becomes 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now, we will be learning more about this constant of proportionality, that is 1 upon 4 pi epsilon naught. In air, in SI unit, the SI unit of K is equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. Now, here one symbol we are finding epsilon naught. This epsilon naught signifies the permittivity of a medium. Now this is a new word. Throughout the unit 1, we will be referring to epsilon naught, epsilon, epsilon r. All these are the permittivities. So let us first begin with the introduction of this word, that is permittivity. Permittivity is the property of the medium which determines the force, electric force between two charges situated in the medium. Minded, it is that property which determines whether the force between the two charges is going to be the very strong or very weak. That is called as the permittivity. So if the charges are present in a medium, the force between them is going to be a weaker one, or it could be a stronger one. That is the deciding factor, is called as the permittivity. Now I hope the meaning of this epsilon naught might be clear to you. If the charges are present in any other medium, then we have the epsilon. So the force between the two charges may vary. It depends on medium to medium. The SI unit of epsilon is this much Coulomb square per Newton per meter square. See here, the unit of epsilon naught and the unit of K, they are reciprocal to each other. So it is very easy to remember these units. So please remember the values and the units, as that can be asked in the exams. Its dimensional formula is this one. This can also be asked as a 1 mark question. So please go for it. Now next, another very important thing in CGS system. CGS means centimeter unit system. The value of K becomes 1. So in CGS, the formula for the Coulomb's force becomes Q1 Q2 by R square. There is no constant of proportionality because its value is going to be 1. So all the important concepts related to Coulomb's law I have explained you. You will write all these concepts. You are going to get full marks in the exam. Don't miss to write all the statements. Next, the topic is unit of charge. In the previous video, I have explained about the electric charges in detail. So there what we have learnt is that as a unit of charge is Coulomb. Now in this video, we will define the Coulomb. What is 1 Coulomb of charge? So for that, in the equation, basic equation, what we have, F equals to 1 upon 4 pi epsilon naught Q1 Q2 by R square. In this equation, if we are going to put the value of charges Q1 Q2 as 1 Coulomb and the distance as 1 meter, so this particular term is going to become equals to the 1. So what we are left with is F equals to 1 upon 4 pi epsilon naught 9 into 10 to the power 9 Newton. So this is a constant value for the force when the two charges are of magnitude 1 Coulomb and are separated by a distance of 1 meter. So based on this statement, we can have the definition of 1 Coulomb is, it is that amount of charge which repels an equal and similar charge with the force of 10 to the power 9 Newton when placed in vacuum at a distance of 1 meter from it. Mind it, here there are certain keywords. What are they? The charges must be present in vacuum. They must be at a distance of 1 meter. The magnitude of charge should be the 1 Coulomb. So there will be a force of attraction or repulsion between them of magnitude 9 into 10 to the power 9 Newton. So if you can give this particular definition. Now in CGS, the unit of charge is ESU, that is called as electrostatic unit, or it is called as the stat Coulomb. Now based on this, we can again define the 1 ESU of a charge. It is that charge which repels an identical charge in vacuum at a distance of 1 centimeter from it with a force of 1 dyne. So in this definition, these two are the keywords. There you have to just change the unit of the parameters. What are they? The two charges must be at a distance of held at a distance of 1 centimeter, and the force between them will become 1 dyne. Then the magnitude of the charge is equals to the 1 Coulomb, where 1 Coulomb is equals to 3 into 10 to the power 9 stat Coulomb. This is the relation between SI and CGS system of unit. So please go for it. This is again another important key point or a concept related to the charge, the Coulomb's law. Next, we have the Coulomb's law in vector form. Now, in vector form, we know that vector is a quantity which is having both magnitude and direction. So, when we are dealing with force, so the direction of force is important. So, in this article, we will be concentrating on the direction of force. Whenever we have the two charges, suppose Q1 and plus Q2, so there the force acting on these two charges will be what? So where various terms that we will be having is F21 and R21. What is F21? F21 is the force on this second charge because of the presence of first charge. Now this first charge will be repelling this Q2. So the direction of this F21 will be in this direction. And R12, what is R12? R12 is the unit vector pointing from Q1 to Q2. If we start moving from Q1 towards Q2, what we will find that we are moving in a direction of R12 position vector. That means the direction of F21 and the direction of F12 are same. So we can have the formula for F21 as 1 upon 4 pi epsilon naught Q1 Q2 by R square. Minded, here this is the magnitude part only. Now since we are dealing in a vector form, So if this side is having a particular direction with the direction of F21, in that direction we are having a position unit vector, that is R12. Here this R12 and F21, they are pointing in the same direction. So this is our balanced equation in the vector form, where R12, that is unit vector, can be represented as vector R upon its magnitude. Next we have F12. What is F12? It is the force on first charge due to second charge. Mind it, here this is the first charge and this is the second charge. They are of similar nature, so naturally they will start repelling. So this is the direction of F12 in this direction, F12, and in this direction what is the position vector? The position vector is that when we are moving from Q2 towards Q1, that is, it is having the direction of R21, which is the unit vector pointing from Q2 to Q1. So what our formula will become? Formula for F12 will become this magnitude part and to R21. So here F12 and R21, they are pointing in the same direction. So this is the formula, and one basic formula we have for F21. Now in the diagram, what we are finding is that the position vector R12 and position vector R21, they are opposite to each other. So we can write unit vector R12 is negative of R21. So now here in this formula of F12, if I replace this R21 with minus of R12. See here minus, because here I am replacing R21 with the sign of minus of R12. Now here what we are having R12, that means it becomes the formula for F21. So F12 is nothing but it is equals to negative of F21, that is force on second due to the first charge. This is how we have derived the Coulomb's law in vector form. I have given all the necessary steps to write this particular derivation, so please go for it. And the important consequence of this Coulomb's law in vector form is that Coulomb's law obeys Newton's third law. This particular statement says that for every force there is equal and opposite force. So it confirms the Newton's third law. That means Coulomb's law in vector form obey the Newton's third law. An important part, F12, that is force on 1, is plus the force on second charge must be equal to 0. Sum of the forces in a particular system will always be the 0. So here these are all the necessary steps for the derivation of Coulomb's law in vector form. In exam, if you will write, you are going to get the full marks. Next we have the concept check. Now let us see. The general question that can be asked in the exam is general question, the repulsive Coulombian force. That is, it is for Q1 is Q2 like is always greater than 0. How we can represent this repulsive Coulombian force? If we have the two like charges, that is two negative charges. This one is the negative charge and this one is also a negative charge. So this is the direction where the repulsive forces will be present. So similarly, we have another like charges, that is two positive charges. So repulsive Coulombian forces will always point opposite to each other. This is how. And Q1, Q2, the product of Q1, Q2 will always be greater than 0. Here see, if we have two minus negative charges, here see, if we have two negative charges, this negative charges, and here this negative charges, negative into negative will become again positive, that is it will be greater than 0. And if we have two positive charges, two positive product of positive charges will become greater than 0. So if this situation is asked, what is the significance of Q1, Q2 is greater than 0? That means we are having the system of two like charges. This is the one concept. Next we have attractive Coulombian forces. For that, Q1, Q2 must be less than 0. Now attractive Coulombian force means the force must be attractive in nature. Now when this force will be attractive in nature? When we have the two unlike charges. That is, if one is negative charge and the other one is positive charge. So here what we are finding, the Coulombian forces pointing towards each other, that is, this is attractive in nature. So whenever it is asked if Q1, Q2 is less than 0, that means it signifies that one of the charge we are dealing is negative and the other charge has to be the positive. Then only this product will give us the attractive Coulombian force. So this is an important concept check related to the Coulomb's law. When the Coulomb's force are repulsive, so with which type of the charges we are dealing, and when the Coulombian force is attractive, with which type of the charges we are dealing. So please keep this in mind. Next is limitations of Coulomb's law. So all the important derivations related to Coulomb's law we have learned. Now there is one limitation. You might be reasoning that it is valid in all situations, but it is not at all. It is valid only under the following condition. Let us see. Whenever the electric charges must be at rest. So this is again a keyword. When the charges are at, then only the Coulomb force exists between these two charges. When the same charges are in motion, then this force, this law is not at all valid. Next is the electric charge must be the point charges. Again, here the term point charges is coming, whose meaning is that the dimension of charges must be much smaller than the separation between them. So that is why the Coulomb's law is valid only in case of the point charges. Next, we have the separation between the charges must be greater than the nuclear size. That means within the dimensions of nuclear size, this Coulomb's law has no application, because there the nuclear forces dominates over the Coulombian forces. So these are the three cases, three conditions under which the Coulomb's law is valid. Now, next is dielectric constant or relative permittivity, another very important topic. Now, see, first of all, what is permittivity? So, permittivity is the property of a medium which determines the electric force between two charges situated in that medium. In the previous article, we have learnt that whenever two charges are placed, there is a force between them. But now here, we will be concerning about the medium in which these two charges are being placed. So what is the role of the medium? With the help of an example, we can find is that the force between two charges located some distance apart in water is about 1/80th of the force between them when they are separated by the same distance in air. What does this statement mean is that, suppose if we are having the two charges Q1 and Q2 that are present in air separated by a certain distance, so naturally a magnitude F, force of F will be present in between these two charges. But when the same two charges are present in a medium, let us suppose the medium becomes water, the magnitude of charges are same, the separation between them is again be the same, everything is same, only the thing is that we have changed the medium, which is water. So now whatever the force is acting between them in water will be 1/80th time that the force which was present earlier between them when they were in air. That means the force is reduced. That means whenever the charges are placed in a medium, the force will be reduced. Now here what I am referring is certain table, a relative permittivity of certain mediums. The first medium is vacuum, whose value is 1. Air we have 1.00054 and in water we have 80. So see here, the medium which is having that much greater electric constant, that much force will be reduced by that much. That is more the relative permittivity, lesser will be the force. That means these two charges will be interacting with the very lesser magnitude in a medium, whereas in air they are interacting with the greatest magnitude. That is what is the concept of relative permittivity is all about. So why the force in the medium is reduced? The force in a medium is reduced because the absolute permittivity of water is about 80 times greater than the absolute permittivity of free space. Here you can find is that the permittivity of water is 80 times that in the vacuum. So more is the relative permittivity, the lesser will be the force present between them. Lesser is the permittivity, more or the strong force will be present between the two charges. This is the concept of the permittivity. So directly, in indirect sense, it gives us the magnitude of the force, how the force is going to be affected when the charges are present in different media. Now, let us find one formula related to this. Whenever the force is present between the two charges in vacuum, we are having a formula F vacuum is equals to 1 upon 4 pi epsilon naught. Here we are dealing with pi epsilon naught and Q1 Q2 by R square. But when the same charges are present in any medium, what the formula will be? F medium. See here, we have to write F medium, which becomes 1 upon 4 pi epsilon. Here the difference is that we are not writing epsilon naught, because epsilon naught is the permittivity of a free space or a vacuum, whereas epsilon is called as the permittivity of the intervening medium. It is called as the permittivity. Yani ki this epsilon is the deciding factor which will decide what will be the magnitude of the force between the same two charges which were there in a vacuum. So what is the effect of this medium? If we will divide these two forces, that is force in vacuum and force in medium, the ratio of these two forces, we will get the ratio of epsilon upon epsilon naught, and this ratio is called as the relative permittivity, which is equals to epsilon upon epsilon naught. So this is also equals to ratio of F vacuum to the F medium. So the definition of relative permittivity, it is the ratio of force between two charges placed some distance apart in free space, ratio of force in free space to the force between the same 2-point charges when they are placed same distance apart in a given medium. So it is the ratio of two forces. So another important concept related to this relative permittivity is that it is a dimensionless and a unitless quantity. Keep in mind, for epsilon naught we have defined the unit in the previous article. In this video only I have given you the unit and the value of epsilon naught, but here for the relative permittivity it is unitless and a dimensionless quantity. It will be having only a magnitude part. So the important concept always what you will find whenever the same two charges are placed in a medium or whether they are placed in a vacuum, the force present between them in a medium will always be less than the force between the same two charges when they are present in the vacuum. That means in vacuum the charges experience the greatest amount of force, and in any other medium the magnitude of the force always decreases. Now I will explain some key points in solving the numericals and some common mistakes that students do in exams. So let's start with the questions that have been previously asked in CBSE boards. Now we will start with the first formula, that is quantization of charge, which is Q equals to NE. About this formula I have already explained in detail, and in this video we will be discussing about how to use this formula in a numericals. Second, we will be using the concept based on the Coulomb's law, that is Coulomb's law formula we will be using. What are the formulas we have learned in the previous topics? That is the formula of force between the 2-point charges present in vacuum, formula between the 2-point charges present in a certain medium, and the relative permittivity, that is epsilon r, which is equals to the ratio of the two permittivities, that is the permittivity in the intervening medium to the ratio of absolute permittivity in the free space. So now let's start with some of the questions that have been asked previously in the CBSE boards. The first question is, let us go for the first question. The question says, which is bigger, a coulomb or a charge on an electron? And how many electronic charges form 1 coulomb of a total charge? So the answer for this question will be the obvious, that 1 coulomb of charge is bigger than the charge on an electron. Let us see how is it. The charge on an electron, all of us know that the charge on an electron is E, that is equals to 1.6 into 10 to the power minus 19 coulomb. That is, it is having a charge of 10 to the power minus 19 coulomb. Now let's calculate the number of charges present in 1 coulomb of charge. So for that we have to use the formula N equals to QE, which is the based on the quantization of charges, that is N equals to Q by E. Here we have to put the magnitude. For Q we will be putting 1 coulomb. For E we have to put its magnitude, that is the numerical value 1.6 into 10 to the power minus 19. On solving this we are going to get 6.25 into 10 to the power 18 electrons. So in 1 coulomb this many number of electrons are present, that is, and there we are having the one charge on an electron is this much of the coulomb. So naturally what we can say is that the number of electrons that are present in 1 coulomb of charge is 6.25 into 10 to the power 18 coulombs. So obviously 1 coulomb of charge is bigger than the charge on an electron. Next question, calculate the charge carried by 12.5 into 10 to the power 18 electrons. Mind it, here what are the parameters that have been given? We have to first concentrate on that. So first of all, here the number of electrons have already been given, that are 12.5 into 10 to the power 8, and we have been asked to calculate the charge carried by this much number of electrons. So which formula naturally we have to use? We have to use the quantization of charges, that is Q equals to N into E. Now the value of E is standard, which is 1.6 into 10 to the minus 19 coulomb. So in this formula, if you will put the value of N, which is 12.5 into 10 to the power 8, which is given, the standard value of E, which is by default, it is always 1.6 into 10 to the power minus 19 coulomb. On solving this, we are going to get the result Q equals to 2 into 10 to the power minus 10 coulomb. That means the charge carried by this much number of electrons will be 2 into 10 to the power minus 10 coulomb. This is how you will have to present your answer in the given format, so that there will not be any chance of losing the marks. So let's have then look at the next question. What is the next question? It says that the two identical charges capital Q each are placed at a distance of r from each other. A third charge small q is placed on the line joining the above two charges such that all the three charges are in equilibrium. This is our key point over here. Three charges have to be in equilibrium. So what will be the magnitude, sign and position of the charge small q? So first of all, we will depict the given situation in the form of a figure. We have to place the two identical charges capital Q and capital Q at the points A and C respectively, separated by a distance of r. Now where the third charge small q must be placed, the small q must be placed in between the line joining the two charges. Then only the system of all the three charges will be in equilibrium. If you place them either to the right side or to the left side, all the three charges will never be in equilibrium. So in order to satisfy the given condition, if q is placed at a distance of x from a and b, then what condition we will be having? The charge will be, the small q will be in equilibrium if the forces exerted on it by the charges at a and c must be equal and opposite. Now when q is placed at a point b, now the charge which is at a and the charge which is at c, they will exert equal and opposite force on the charge small q. Then only the small q charge will be under the equilibrium condition. On putting the magnitude part in the formula, what we will get, this is the force between the charges at the point A and B, and this is the force which is present between the charges at point B and C. This is B and C. They are separated at a distance of r minus of x. Why? Because the total distances are, out of which the distance between A and B is x. So what will be the remaining distance? The remaining distance B and C will become r minus of x. So this is the two forces that are present on a small q charge because of the charge at A, and this is because of the charge at C. On cancelling the like terms, what we will get? On this term, and on solving the term, we will get the position of a small q must be at r by 2. That is, the small q must be placed at the center of the line joining the two charges. Now the key point must be in order to find the sign of a small q. Now how we can find the sign of a small q? The sign of a small q we can get by considering a concept that if capital Q is to be in equilibrium condition, if capital Q is in equilibrium condition, that means the two forces which are present on capital Q must cancel each other. Now what is the force which is acting on the charge which is present at A? The C charge will be repelling this charge in this direction. The charge at C will be repelling the charge at A in this direction. So the charge at B, which is a small q, must attract the charge at A, so that the charge at A will become in equilibrium condition. So the charge at A is under the two forces. One is the attractive force by the small q, and one is the repulsive force exerted by capital Q. This is the key point. This is the key point or the deciding factor which will decide what should be the sign of small q. So the sign of small q has to be opposite to that of the capital Q. Then only the system of all the three charges will be in equilibrium. If you will take the sign of small q as same to that of capital Q, then the three charges will never be in equilibrium. Keep this key point in mind, that if the system of three charges are in equilibrium, the third charge has to be in opposite in nature. So now after that, our given condition will be force of repulsion between A and C must be equal to the force of attraction between A and B. So the repulsive force between A and C, that is repulsive force between capital Q, and the force of attraction by the small q must be same. That is, on putting the magnitude form, we can get this cancels out. So what we are left with, q equals to q by 4. So this is the magnitude part. What is the sign of the small q? Sign of this is just opposite. Here, mind it, here we are not mentioning the sign of q is positive or the sign of q is negative. We are not mentioning any of the sign. We are just mentioning whatever be the supposed sign of the capital Q, the opposite sign must be carried by the small q. That should be your answer, not in a way that it should be positive or negative. This is the key point where you have to give the stress. The sign must be opposite to that of capital Q. Now next question, let's say another question which is again based on the condition of equilibrium. Now 2 point charges of charge values capital Q and small q are placed at a distances of x and x by 2 respectively from a third charge of value 4q. All charges being in the same straight line. Now calculate the magnitude nature of capital Q charge such that the net force experienced by the charge q is 0. Here we have to take the two conditions. One is of capital Q charge and the other one is of the small q charge. Keep this in mind. In the previous question, we were having the equilibrium condition when all the three charges were in equilibrium. Here only a small q charge is in equilibrium. So let us see first of all how the three charges can be placed. The three charges we are placing according to the figure. Here from a charge 4q which is placed at A, the capital charge q which is placed at B is at a distance of x, and the another charge small q which is placed at a distance of C at a distance of x by 2 from 4q. Now what will be the key point over here in solving the question? For the equilibrium of the charge small q. Now according to our question, small q charge is at equilibrium. Under which condition it will be equilibrium? When it is under the experience of two equal and opposite forces. Now C will experience a force from A and C will experience a force from B, and these two forces must be equal and opposite, that is FA and FB must be equal and opposite. So what we can depict is that the charge on capital Q must be same as that on the charge of 4Q. Then only the C will be under the action of two equal and opposite forces. So what will be the sign of capital Q? The sign of capital Q must be the same. Here again we are not mentioning that the sign should be the positive or sign should be the negative. Here we are just mentioning the sign of capital Q, which is at B, must be similar to the sign of 4Q, which is placed at A. So this one will be your key point. It is not opposite, otherwise the charge at C will not be in equilibrium. Now again, so according to our this key point condition, FA must be equals to FB. Now we have to put the Coulomb's law. What is that? X by 2 and X by 2. We have to put the formulas over here. So both of them are at a distances of X by 2 and X by 2. So like terms get cancelled out and we will get the magnitude of capital Q as equals to 4Q. So here again the concept we dealt with is the condition of finding the based on the equilibrium forces, based on which we have found the sign of the charge and the magnitude of the charge. Now any question which is based on such concept will be asked, you must be able to give the answer. Try to go for some more questions. In the coming slide I will give you some questions. Please try to solve it. Let's go for solving some questions previously asked in CBSE based on these topics. So here are these questions. In case you find any difficulty in solving these problems, please do mail me at this ID. I will provide you with all the solutions. Hi to all Braineryans. Next we are having our next topic is principle of superposition, that is forces between multiple charges. In Coulomb's law, we have dealt with the force between 2 point charges. Here in principle of superposition, what is the statement? It states that when a number of charges, now here we will be dealing with the number of charges that are interacting, the total force on a given charge. That means the total force on a single point charge is the vector sum of forces exerted on it due to all other charges, So now let us try to understand the meaning of this statement. It seems quite complicated, but let us see it. I will make it very simple one. Suppose we are having number of charges. What are they? Q1, Q2, Q3 and Q4 that are interacting in vacuum. That means they are present in vacuum. Now, so we want the total force on a given charge. That means for simplicity, if we want the force on a Q1 charge, that is on a single charge Q1, what it will be? Q2 will be exerting a force on Q1 which will be in this direction and it is denoted by F12. Its direction is this one. Similarly, Q3 will be exerting a force on Q1 which will be F13. It is in this direction. Now Q4 will also be exerting a force on Q1 which is in this direction, that is F14. So if we want to find the total force on Q1, according to the statement, what it will be? It will be the vector sum of the total forces, that is vector sum of F12, F13 up to Fn. That is whatever the forces are acting on this Q1, they have to be added vectorially. Mind it, vectorially they have to be added, not algebraically. About vector addition, you would have learnt in 11th class. So we have to apply here the vector addition of all the forces. Now, I think the statement would be clear. What it says that when a number of charges are interacting, the total force on a given charge is the vector sum of the forces exerted on it due to all other charges. Now, what is the next statement? The force between two charges is not affected by the presence of other charges. It's a very important concept. That means the force between two charges. Let us see. For example, we take F12. This is the force between Q1 and Q2. This force F12 will not be affected by the presence of Q3 charge and Q4 charge. That means whatever be their magnitude or whatever be their sign, Q3 and Q4, whatever sign and magnitude they are having, the magnitude of F12 will not be affected by the presence of Q3 and Q4. Similarly, if we deal with F13, if we will be calculating the formula for F13, we will find that F13 will not be affected by the presence of second charge Q2 and Q4. That is, whatever be their magnitude or sign, F13 will not be affected by Q2 and Q3. Similarly, if we are dealing with F14, which is the force between Q1 and Q4, this F14 will not be affected by the presence of Q2 and Q3. It remains unaffected. That is, the force between two charges is not affected by the presence of other charges. Whatever n number of charges we are having in space, the individual force that is between Q1 and Q4, between two charges, will not be affected by the presence of other charges. Next, we are having the mathematical formulation of this principle of superposition using Coulomb's law. Let us see what we can do. For that, let us try to understand the simple figure. Here, what we are having, the n point charges, that is Q1, Q2, Q3. Q1, Q2 and Q3, they are placed in vacuum, and with respect to origin, their position vectors are R1, R2 and R3 respectively. Now, this Q2 will exert a force on Q1 in this direction, which is F12. Similarly, Q3 will exert a force on Q1, which is F13 in this direction. Now, only two forces are acting on Q1, that are F12 and F13. So, what will be the total force F1? It will be the vector sum of F12 and F13. So, for that, let us try to find out the magnitude and the value of F12. So, according to Coulomb's law, what will be the formula for vector F12? From the article Coulomb's law in vector law, I have already explained this concept. You may refer to that video. Here, vectorially, the Coulomb's force will become 1 upon 4 pi epsilon naught Q1 Q2 upon R12. So, what is this R12? R12 is the unit position vector between Q1 and Q2. The meaning of this statement I have already explained in my previous video. If you have any doubt, you may please refer to it. Next, we want F13. F13 is the force between Q1 and Q3. So, its magnitude by the help of Coulomb's law in vector notation, it will become 1 upon 4 pi epsilon naught Q1 Q2. It will become Q1 Q3 upon R13 whole square. R13 square, where the unit vector will be pointing from R13, that is Q3 to Q1. So, this one will be R13 and this one will be F12. According to the principle of superposition, now we will add these two forces vectorially. So, what will be the net force? F1 will be the vector sum of F12 and F13. So, this is all about your principle of superposition. Next, we have certain key points. So, what are the key points for this particular figure? That is for the principle of superposition. First key point is Coulomb's law gives us force between 2 point charges. So, Coulomb's law is dealt with 2 point charges, whereas principle of superposition enables us to find out the force on a point charge due to a group of point charges. That means if we are having a number of point charges Q1, Q2, Q3, Q4, whatever the number of forces, that is F12, F13 and F14, these forces can be computed on a single point charge. The third is, this principle is based on the property that the forces with which two charges attract or repel each other are not affected by the presence of other charges. That means, the meaning of this statement I have already explained earlier. Let's see it again. That means F12 will not be affected by the presence of other charges, that is Q3 and Q4, whatever be their magnitude or sign. Similarly, F13 will be unaffected by the presence of other charges, that are Q2 and Q4. Similarly, F14 will not be affected by the presence of Q3 or Q2. So, these are the key points. Next, go for the numericals. So, first numerical based on this article is, consider three charges Q1, Q2, Q3 each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge capital Q with the same sign as small q placed at the centroid of the triangle? So, for this question, let us try to understand what the figure is, what the figure can be. So, first of all, we are having an equilateral triangle. So, suppose A, B, C, it is an equilateral triangle of side L, L and L. Next, the Q1, Q2 and Q3. So, Q1, Q2 and Q3, they each are equal to Q, Q and Q. They are placed at the vertices of A, B and C with the position vector, that is, now O is the centroid. At the centroid, what we are placing, we have placed a capital charge Q. So, suppose at the centroid capital Q is placed with the same sign as that of the small q and small q. So, what will be that? We want to compute the force on capital Q. So, for that we should know the distance between AO, the distance between BO and distance between CO. So, AO distance will be equals to, let us suppose, R. Similarly, BO distance will be in this direction, it will be also equals to R. Similarly, CO, which is in this direction, it is also equals to R. So, we have got all the distances. Now, let us calculate the force on charge capital Q due to Q1. So, now Q1, which is placed at the point A, it will be exerting a force of F1, which is in the direction of AO. So its magnitude we can find with the help of Coulomb's law, which will be 1 upon 4 pi epsilon naught q1 upon AO square, where AO square is the distance between the 2 point charges. Here we have taken in general notation. After that we will put their respective values, and it is and in this AO is the unit vector pointing from A to O. Similarly, if we will find the force on charge capital Q due to Q2. Now where Q2? Q2 is at the point B. Now this Q2 will exert a force F2 which will be in this direction, and its formula we can have 1 upon 4 pi epsilon naught Q2 upon BO square, because the distance between Q2 and capital Q is BO and its unit vector will be along BO. Similarly, what is the third charge we are left with? So it will exert, that is this charge at C, that is Q3, will exert a force of F3 in this direction, whose magnitude will be 1 upon 4 pi epsilon naught Q3 upon CO square, which is in the direction of CO, and unit position vector will be CO. So there we have got the formula according to Coulomb's law. Now on applying the principle of superposition, what I have said it earlier is that total force on this capital Q charge, which will be F. So what will be the formula? It will be the vector sum of F1 plus F2 plus F3. Now let us see what will be the vector sum. So we have to add all the formulas, that is F1 plus F2 plus F3. If we go for their magnitude wise, they are all equal, that is capital Q into Q. Why? Because Q1, Q2 and Q3, they all are equal to Q. So for that we can place them as Q. Upon 4 pi epsilon naught. What is AO, BO and CO? AO, BO and CO, already we have assumed that their distance are same, that is equals to R square. So now here we have put the values of Q1, Q2, Q3 and that is AO, BO and CO. After that here vectorially we have to add. So the unit vector AO, unit vector, unit position vector BO and unit position vector CO, they are being added. Now next, what concept we are having? Angle between each pair of unit vectors AO, BO, CO, that is AO is in this direction, BO is in this direction and CO is in this direction. The angle between them is 120 degree and they all form a triangle of cyclic vectors. About this concept you would have learnt in 11th class. So the triangle of a cyclic vectors always add up to 0. So what conclusion we are getting? The unit vector, the sum of unit vectors AO, BO and CO will be equals to 0. So this particular term in our equation, it will become equals to 0. So net force will become equals to 0. So this one will be our answer. The net force on capital Q charge, which is placed at the centroid of an equilateral triangle, it will be equals to 0. So please go for all the steps I have given in a very nice way, so you may be able to understand it very clearly, and if you will write all these steps, there are no chances of losing any marks. Next, go for the second question. Consider the charges Q, Q and minus Q placed at the vertices of an equilateral triangle as shown in the figure. What is the force on each charge? So let us see what the figure has to say. So here we are having Q, Q, Q. That means they are equilateral triangle. We are having A, B and C. So is Q, let us for simplicity we have taken Q1 is the charge, Q2 is the charge having the magnitude positive Q and positive Q, and Q3 which is placed at point C, it is having a magnitude of minus Q. They are placed at the vertices. Now equilateral triangle, that means the side of the equilateral triangle is L, L and L. Next, the forces of attraction or repulsion. Now let us see whatever is the force acting on the point charge placed at A. Now the force which is acting on the point charge A, it will be under the repulsive force due to the charge at B. That means because they are of the same sign. You will find Q1 and Q2, they are of the same sign. So this Q2 will exert a force in this direction which is of magnitude F. Similarly, now Q3 which is placed at C, its magnitude according to our question is minus Q. So this negative charge Q3 will attract the charge at A, that is Q1, in this direction. So this will be the force on A due to the negative charge. So if we want to compute the force on Q1, its net force will become F1 and their magnitude will be the FF magnitude. That is, it is acting at a distance of L whose point charges are Q and Q. So what will be the magnitude? It will become 1 upon 4 pi epsilon naught Q square by L square. The point charge at A is under the force of attraction due to Q3 and it is under the action of repulsion due to the charge at B, but whose magnitude will be 1 upon 4 pi epsilon naught Q square by L square, because the separation between these charges are L and L. Similarly, if we want to find the force acting on B, so the B will be under the repulsion force of due to A, which is in this direction, and the attractive force F will be acting in this direction, whose magnitude will be the same one. Similarly, if we want to compute the force on charge C, which is Q3, that is negative. Now, negative charge will be attracted by the charge at A and it will be attracted by the charge at B because they both are positive. But magnitude will be the same, which is F, because they are separated at a distance of L and their magnitudes are Q and Q. So, again the formula will be, so this is force of attraction and repulsion. Whether we are having attraction or repulsion, the magnitude will be the 1 upon 4 pi epsilon naught q square by L square. So this is the general computed formula we have just derived. Now we will go for the vector addition. Now by parallelogram law, net force on Q1. Now we want to find the net force on Q1, which is F1. Now this F1 will be the vector sum of this F and this F. Two F's that are acting and their angle between them, because they are exterior angle to the equilateral triangle, so it will be 120 degree. So vector addition if we will apply, so what will be the magnitude? Under root of F square plus F square plus twice of FF cos 120 degree, and its direction will be pointing along BC. Mind it, here they are pointing in this direction, which is the direction of BC. On solving this, putting the value of cos 120 degree as minus 1 by 2, what we will be having is that under root of, we will be having 2f square minus of f square. We will be left with this term. So it becomes simply the under root of f square. On removing the under root, we will get f and simply f, and the direction will be along BC. This is acting along the BC side of a equilateral triangle. So this is the magnitude as well as the direction, the force acting on the F1, that is Q1 charge. Similarly, by parallelogram law, net force on Q2. Now let us see what is the net force on Q2. So the net force on Q2, we are finding it is under the action of one, this repulsive force, and another one is the attractive force, whose magnitude already we have given. So again, by applying the same parallelogram law by this vector addition, the magnitude, the angle between these two forces is again 120 degree. So again, we are going to get, by solving the same step, we will get the formula for F2 as F, but the direction this time will be along the AC side of this. See, this is the direction of F2, which is along the direction of AC of the equilateral triangle. Next, we want to find the force on Q3. So net force on Q3. Now Q3, it is under the action of two attractive forces F and F. They are acting at an angle of 60 degrees. So here we will again apply the vector law of addition. This time F3 will be under root of F square plus twice of FF. This is cos 60 degree. Now by putting the value of cos 60 degree and solving this equation, we will get the answer as root 3f, and it will be pointing in this direction, which is suppose unit vector, normal vector, and its direction we have to mention. So this is how we have calculated the force on each charge. So what are they? F1 will be F in the direction of BC. F2 will be again equals to F, whose magnitude it will be this much. You can put the magnitude this much, but direction you have to mention it is along AC. Similarly, for the force on F3, that is F3 force, it will be the root 3 times of this magnitude. So mind it, here for F, you have to put this value 1 upon 4 pi epsilon naught q square by L square, and its direction will be unit vector, normal vector, which is pointing in this direction. With this, we have solved this question. I hope you would have understood and go for all the steps. Let us go for our next question. The next question says that 4 equal point charges, each 16 microcoulomb, are placed on the 4 corners of a square. Now this time this is a question based on a square. Earlier we were having for the equilateral. For the 4 corners of a square of side 0.2 meter, calculate force on any one of the charges. So let us depict this particular figure. How we can say, let us suppose we take a square ABCD and calculate the force on any point charge, suppose which is Q4. So let us take the how to see the figure A, B, C and D. This is a square on which we have placed a charge Q1, Q2, Q3 and Q4, each of magnitude 16 microcoulomb. Now the side of the square is 0.2 meter and everywhere we are having 0.2 meter. Now if we want to calculate the charge on Q4, now the Q1 will be exerting a force on Q4 in the direction of, that is AD, which is called as the F1 force. So first of all, we will calculate the magnitude of the force exerted on Q4 by Q1. How to find this magnitude? We can find this magnitude by the help of Coulomb's law, which says that 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now this is the standard formula. Throughout our video, I have been referring to this particular formula. So this time I am directly putting the values. So what we are having? 1 upon 4 pi epsilon naught is 9 into 10 to the power 9. Q1, Q2. Here we are having Q1 and Q4. That means the two charges whose magnitude is 16 into 10 to the power minus 6 coulomb. Here we have converted the 16 microcoulomb to the SI unit. So we have to put 16 into 10 to the power minus 6 and again 16 into 10 to the power minus 6 upon R square. So what is R square? R square is the distance between the 2 point charges. So here the distance will be the between A and B, which is 0.2. So we have to do the 0.2 ka whole square. On solving this part, we will get the value 57.6 Newton and it's in the direction along AD. So we have to mention the direction as well. Next, we will calculate the force exerted on Q4 by Q2. Now where we have placed Q2, Q2 is placed on the point B. Now what will be the formula? The formula again will be based on Coulomb's law. So here 1 upon 4 pi epsilon naught we will put as 9 into 10 to the power 9. Q1, Q2, that means the value of Q2 and Q4 we have to put, that is 16 into 10 to the power minus 6 and 16 into 10 to the power minus 6 again upon R square. Now this time how to calculate this distance between the two charges, that is BD. Now we know that this BD is the hypotenuse side of a right angle triangle BDC. So this side BD will be equals to the, we know by using the hypotenuse theorem, it will be equals to the 0.2 whole square plus 0.2 whole square. That will be the under root of, using the Pythagoras theorem, by using the square of BC square, under root of BC square plus DC square. So we will put the magnitude 0.2 square plus 0.2 square. So this value we have put, and if we will do the square of this distance, we will remove the square root. So we will get 0.2 square plus 0.2 square. On solving this magnitude part, we will get the value as 28.8 Newton. Now the direction of this F2 will be along BD. So here we have to mention that its direction is along BD. So now I think F1 this direction and F2 these two forces will be clear to you. Next we will calculate the force exerted on Q4 by Q3. Now where we have placed Q3? Q3 is placed at the point C. So again by using the Coulomb's law formula, what we can have, that is Q1 Q2 by R square. So 9 into 10 to the power 9 we have to put, Q1 Q2 the same magnitude to put, and the distance between D and C is again 0.2 ka whole square. So we will solve this part and we'll get 57.6, the same value as F1, and this F3 will be pointing along the CD direction. So here F1 and F3, they are equal in magnitude but their directions are perpendicular to each other, that is F1 and F3 are perpendicular. So what will be the resultant? So mind it, here the resultant will be along this particular between the F1 and F3. How to get the magnitude part? Under root of F1 square plus F3 square, that we all know how to get the resultant of two perpendicular vectors. So by putting the magnitudes of 57.6 whole square plus 57.6 whole square, we will get the value as 81.5 Newton, whose direction will be along BD. Now mind it, here the direction will be along B to D. Now along B to D already one force F2 is already present, and now another force will be superimposed on F2, which is the resultant of F1 and F3, that is this F dash force will be superimposed on F2. Then only we will get the net force on Q4. That means what will be our next step? Total force on Q4. Now this will be the final part of our answer. So total force is F. How we can get? It is simply by the algebraic addition of F2 plus F dash, because both the two forces are acting along the BD direction. F dash as well as this F2 is also acting along the BD direction. So we have to simply add, that is this magnitude 28.8 Newton and this 81.5 Newton we have to add, and by adding we will get this value, and the net direction is along BD. I hope with this particular equation question the concept of superposition of principle might get clear to you.